Okay, so in this lecture, we're going to talk about the limiting behavior of a sequence of random variables. Okay, so we are going to deal with a sequence of random variables. So each random variable is a function that maps the outcome to a real number. So it is a sequence of functions. And this is very important because later on when we talk about stochastic process, we are going to deal with the sequences of random variables. Okay. So last time we have presented a example where we look at a binomial distribution. So Yn follows a binomial NP distribution. So we are looking at n experiments, and each experiment succeeds with probability P. And all these experiments are independent, IID. So Yn denotes the number of success that we observe in these n experiments. Now we know that Yn follows a binomial distribution. And empirically, we found that, okay, if we fix the success rate and let the number of total number of experiments n go to infinity, then this distribution, the PMF of this random variable converges to a Gaussian distribution. In fact, a normalized version of Yn, right? Yn subtract the mean divided by the standard deviation. This random variable converges to a Gaussian distribution empirically as the total number of experiments goes to infinity. Okay? We call this the Gaussian approximation of binomial distribution. Okay? So basically, if we perform more and more number of experiments, then this Yn we can basically use in Gaussian PDF to approximate the PMF of this binomial random variable. Because you see that for the binomial distribution, it is more complicated because it involves a lot of combinatorics. But for Gaussian, it is a very simple exponential-like distribution. So this Gaussian approximation is very accurate when n times p is much larger than 1. Okay. So in this case, we fix p and let n go to infinity. So n times p goes to infinity. But in practice, we will use this criterion to determine whether or not to use the Gaussian approximation. So let's look at one particular example. Let's flip a fair coin 10,000 times. Okay. Now, since it is a fair coin, so for each toss, we will observe a head and the tail equally likely. So the success rate is 1/2. Okay, and we perform this experiment 10,000 times. And then we are interested in the total number of heads observed within these 10,000 trials. And we want to calculate the probability that the number of heads in these 10,000 trials is between 4,900 and 5,100. Now we expect that so if we perform 10,000 experiments, we expect that the number of heads is concentrated around 5,000, right? Because the success rate is 1/2. So 1/2 times 10,000 is about 5,000. And to quantify this event, the probability of this event, okay, we can consider using Gaussian approximation. Okay. So first of all, we know that, let's denote this total number of heads as Yn, and we know this random variable follows the binomial distribution. Okay, it's a standard binomial distribution setup, where the success rate P is 1/2, and the total number of experiments that we are looking at is 10,000. And in this particular case, we observe that n times P is 5,000, right? N times P. This product is far bigger than 1. So in this case, we know that Gaussian approximation is going to be very accurate. So basically, this binomial distribution can be well approximated by Gaussian distribution. So how do we characterize this using Gaussian distribution? Well, we look at, for Gaussian distribution, we need the mean and variance. So that's basically the two statistics that we need. So here, we can characterize this, the mean and variance of yn. Because it's a binomial distribution, so we know the mean is n times p, which is 5,000, right? So we expect to observe around about 5,000 heads. And the variance of yn, according to the binomial distribution, is np times 1 minus p, okay? And it is actually 2,500. So the variance is very small compared to the mean, which means such a distribution is going to be very highly concentrated around the mean. Okay. Now, given these two statistics, and given the fact that NP is far bigger than 1, we can consider approximate Yn using a Gaussian distribution that has mean 5,000 and variance 2,500. So basically, we are looking at the probability of this event. So Yn is between 4,900 to 5,100. And since now we are approximating Yn using Gaussian distribution, so we can consider dual normalization. So Yn, let's subtract the mean divided by the standard deviation. Now the mean is 5,000, standard deviation is the square root of the variance. Now, after this normalization step, this normalized Yn by the Gaussian approximation, this normalized Yn can be approximated by a standard normal Gaussian random variable, right? Zero mean unit variance. So we can view this random variable z as a standard Gaussian random variable. Okay. And then the probability of this event is the probability that z is between -2 and 2. Z is between -2 and 2. And now this z is approximated by a standard Gaussian random variable. So this can be, the probability of this event can be expressed in terms of the CDF function of standard normal Gaussian. So it's a phi function, it's phi2 minus phi -2. And by looking at the table of phi functions, we can calculate that this is approximately 0.95, right? So basically, with about 95% probability, the number of heads that we observe is between 4,900 and 5,100. Okay, so highly likely we are going to observe around 5,000 number of heads in this experiment. So this is the concentration phenomenon of random variables. And you can imagine that if you let this n goes to infinity, or instead of having 10,000, let's do 1,000,000 experiments, then this probability is going to be closer to 1, okay, maybe 99% probability. So this is the case when this binomial distribution, when this product n times p is far bigger than 1. This is the first regime. And the other case that we care about is when we have when we increase the number of experiments, the success rate decreases. Okay, so that their product remains a constant. So so in this case, n times p is not far bigger than 1. Instead, this product remains a constant. Okay. So in this case, we cannot use the Gaussian approximation, right? The Gaussian approximation says that this n times p must be far bigger than 1, but this is not the case in this regime. So in this case, when this product remains a constant, we can still look at some basic statistics of this binomial distribution. So the expectation, we know that is n times p, but now this product is a constant. So basically, the expectation is essentially lambda, and the variance is np times 1 minus p. Now you by leveraging this constant product, we can simplify this. So n times p is lambda, and the 1 minus p, well, p is lambda over n. Okay. So we can see that the variance is lambda times 1 minus lambda over n. And as n increases, because in this case, n is increasing and p is decreasing, right? But the product remains the same. So the variance is depending on lambda and also the total number of experiments, n. So as we increase n, this number is going to converge to 1. Okay. So the variance is going to converge to lambda as n goes to infinity. So basically, we can see that in this case, in the limit, the binomial distribution is going to have a constant mean, which is lambda, and also a constant variance, which is also lambda. But compared to the first case, the previous case, in this case, the mean, and we have this mean and variance. But here we are fixing p and let n goes to infinity. So the mean is going to goes to infinity because it's n times p. And also the variance is also going to goes to infinity, right? Because p is fixed, n goes to infinity. But in this second case, the product remains a constant. So both the mean and variance is going to converge to a constant value lambda. So this means the limiting behavior of this binomial distribution in this case is very different from the previous case. And it turns out that in this case, the binomial distribution can be well approximated by Poisson distribution. It's not Gaussian. So here we have a result that basically says that, okay, if n times p goes to a constant lambda, so basically as we perform more and more experiments, the success rate p decreases, so that n times p remains a constant in the limit. In this case, the binomial NP distribution can be, so this distribution converges to a Poisson lambda distribution. Basically, the PMF of Yn can be approximately calculated by the Poisson distribution. Okay. This is the standard Poisson distribution with parameter lambda. Okay. Now this lambda parameter is determined by the limit of this product. So once you know this lambda, you can approximate this binomial distribution using this Poisson lambda distribution. So this approximation is accurate when the product is a numerically small constant. For example, n times p is 0.1 or 0.01. Then this Poisson approximation is going to be very accurate. And this is an empirical experiment that shows that. So in this case, I think the n is set to be 1000 and the product, so n times p is set to be 20. So basically p is lambda over n. So p is 20 over 1000. That's the success rate. And we can see that these two curves, the solid red curve, which is the empirical distribution of Yn binomial distribution, the dashed black curve is the Poisson PMF. So they match very well. And this is basically a short proof of this statement. The general idea is this: we first look at the distribution of the standard binomial random variable Yn. Right? So this is the expression for the binomial distribution. It's n choose k where we observe k success and n minus k failures. So this is the binomial distribution. And the rest of the step, okay, and the second step is to express this combinatorics using this is n choose k. So n choose k, we have this many number of possibilities from the previous lectures. And p in this case is lambda over n. Okay. And the rest of the steps is simply to rearrange all these terms so that in the end we can see that the limit is actually. So this is the limit. Okay. We have several terms. This term goes to 1 as n goes to infinity, because n is in the denominator. Lambda is a fixed. Lambda and k, they are fixed. N goes to infinity, so this goes to 1. And this is a standard. This goes to e to the power of negative lambda, the standard limit in calculus. This goes to e negative lambda, and this is a constant coefficient. So we can see that in this case, indeed, this binomial distribution converges to the Poisson, a standard Poisson distribution. And we can consider another example. So let's say a system has 1000 components, and each component may fail independently with probability 0.001. We want to find the probability that no components would fail within 1 month. Okay. So again, this is a standard binomial distribution. Right? We can define Yn to be the number of failed components. And because we have 1000 components, each component fails with this probability. So this Yn is a standard binomial NP distribution. N equals to 1000, P equals to 0.001. Okay. And this event, the probability, this event equals to can be expressed as yn equals to 0. Right? So the number of failed components equals to 0, meaning that no components fails. So basically, we're looking at probability that yn equals to 0. And since we are looking at a large number of components and with a certain failure probability, we can consider using some approximations to approximate this binomial distribution. Okay. So there are several ways to calculate this probability, to approximately calculate this probability. The first way is to calculate this exactly. Because we know the binomial distribution, we can calculate this probability exactly. So following the binomial distribution, this is yn equals to 0, right? So you simply replace k here, replace k by 0 in the binomial distribution. So doing that, this k is 0, so it's n choose 0, and p to the power of 0. This is 0 failures and n successes. And calculating this one, so you have n equals to 1000, p equals to 0.01. So plug in all these parameters into this distribution, you get 0.36. So it's about 36% probability. So this is the exact value, the accurate one. And since we have introduced two different approximations, one is Gaussian, one is Poisson's approximation. We can use these approximations to calculate this probability, see which one gives a more accurate result. So in this case, we observe that this product n times p equals to 1. Okay. If we want to use Gaussian approximation, this product is better to be much bigger than 1. But in this case, it is not much bigger than 1. It is equals to 1. And this means that if we use Gaussian approximation, the result may not be accurate. And let's see if this is indeed the case. So we can try to approximate this one using the Gaussian approximation. So the Gaussian approximation says that we can consider this normalized yn as a standard Gaussian random variable. And then let's look at the probability of yn equal to 0. This is the original probability that we are looking at. And because yn has to be bigger than or equal to 0, so yn is the number of failed components. It must be non-negative, right? So this is equivalent to say that yn is less than or equal to 0, because yn can never be negative. And by doing that, we actually transform this probability into a CDF function of yn evaluated at 0, right? And for this CDF, we can approximate it using Gaussian approximation. So we do a normalization on both sides, right? Subtract the mean divided by the variance, standard deviation. And in the Gaussian approximation, we view this as a standard Gaussian random variable. So this entire probability can be calculated using the phi function. Okay. Phi function, CDF of this standard Gaussian random variable. And it turns out that if you plug in n and p in the right-hand side, it gives this value. So it's the phi evaluated at this value, at this point. And you can numerically calculate this value. It is about 15.8%. And you can see that it is far from the exact result. So this indeed verifies that in this case, Gaussian approximation is not accurate because NP, this product, it is not far bigger than 1. So instead, we can consider using a Poisson approximation because here we observe that NP, N times P, is a relatively small number. So maybe Poisson approximation is more accurate. So following the Poisson approximation, so the Poisson approximation says that, okay, this probability can be calculated. So we can approximate Yn using a Poisson lambda distribution. Okay? And the lambda is the product, which equals to 1 in this case. So basically, this probability can be approximated by this Poisson lambda distribution. Because we are looking at k equals to 0, so we plug in k equals to 0 into the Poisson lambda distribution. So this and this denominator part, both of these two parts equals to 1. So we only need to calculate e to the power of negative lambda. The lambda is 1 in this case. So it's essentially e to the negative 1. And if you calculate it, it is about 36.8%. Okay. So this is much more accurate. It's very close to the exact result. So it's much more accurate compared to the Gaussian approximation. Okay. So basically, depending on this product, we may consider, if this product is far bigger than 1, we consider using Gaussian approximation. If this product is very small, numerically very small, then Poisson approximation is a much better choice. Okay. So from these examples, we can see that indeed, this is a simple example about binomial distribution, right? So here we're looking at a sequence of binomial random variables. Well, as we perform more and more experiments, this random variable Yn, the behavior or the distribution behavior of this Yn is getting closer and closer to certain special distributions. So this motivates us to further study the limiting behaviors of a sequence of random variables. And next, we will formally introduce several different types of convergence of random variables. And these are very important and useful concepts. They are a little bit advanced, but they are the very basic and fundamental concepts for studying the random process. So here, the basic setup is that we are going to consider a sequence of random variables, xn. So this sequence is indexed by n. Each xn is a random variable. So you can view each xn as a random variable that in a certain probability space. We have outcome, sigma algebra, probability measure. So basically, each xn maps outcomes to a real number. It's a function, it's a real valued function on the outcome space, omega. So it's the basic setup of probability. And here, to simplify the discussion, we will consider the outcome space to be the unit interval between 0 and 1. And the sigma algebra is the Borel sigma algebra generated by open intervals on this omega space. Right, so we have introduced this basic setup in the previous lectures when we talk about uncountable continuous outcome spaces, or basically uncountably infinite outcome spaces. Right. So the basic setup is that omega is the unit interval. Well, but this includes uncountably infinitely many number of real numbers, right? And we are looking at the sigma field that we are looking at is the Borel sigma field, which is the sigma field generated by the countable unions, countable intersections, complements of open intervals. And the probability measure defined in this setting is that for any interval n between a and b, the probability measure is simply b minus a. It's very simple probability measure. And we are looking at the convergence behavior of xn. So this is a figure that illustrates this sequence of random variables. The x-axis is the outcome space. So here we are looking at the interval between 0 and 1. Right? So this interval is the omega space. And all this sequence of random variables, x1, x2, they are simply functions defined on this outcome space. So for example, x1 may look like this, right? It is a function defined on omega or over this interval. For different omegas, it may respond different values. That's the realization of these random variables on this outcome. And x2 omega may behave a little bit different. It may be a different function defined on this omega space. And we have a sequence of these functions that we can draw on this graph. And we want to study how is this sequence of functions going to converge in the limit as n goes to infinity. Okay. So next we are going to talk about convergence different types of convergence of random variables. And before that, we can recall some basic the basic convergence definition of a sequence of numbers that we introduced in calculus. So let's consider, first of all, let's consider a sequence of real numbers, right? Small xn. Each xn is a number. We say that this sequence of numbers converges to another real number x. Right? So the notation that we use, so we have a sequence of numbers, real numbers, right? And when we write down this notation, limit xn equals to x. This is a notation to denote that this sequence of numbers in the limit converges to a certain number x. For example, if xn equals to 1 over n, then we know that this xn goes to 0 as n goes to infinity, right? So we will write limit 1 over n equals to 0. But what does this precisely mean mathematically? This is just a notation to express this convergence behavior, limiting behavior. We need a very precise definition, and this is precisely defined using the epsilon delta language. I think here's epsilon. Okay, it's epsilon delta language. Precisely, it means that. Now here's the precise statement. Let's look at that. Precisely, it means that if we look at any epsilon, any deviation epsilon, so basically, epsilon can be arbitrarily small. You can always find an epsilon So let me write this here. So for any epsilon bigger than 0, right, you pick any arbitrary small epsilon. Epsilon could be 10 to the power of -10, could be 10 to the power of -100. Pick any arbitrary epsilon. There always exists a threshold that depending on this epsilon. Okay? No matter how small the epsilon you pick, I can always find an integer, an epsilon that depends on epsilon, such that for all bigger than this threshold, we have the deviation between xn and x is smaller than this epsilon. So intuitively, this means that no matter, now you set a threshold, you set a deviation threshold epsilon first. No matter how small this epsilon is, I can always find, or put it in another way, the sequence is going to be eventually getting closer to this x within epsilon. Right? And eventually means that after a certain point, for all the sequences after that point, they will get, the entire sequence will be epsilon close to the target x eventually, right? So for all the sequences n, sequence index n, after this capital N epsilon, the entire sequence will be within the epsilon neighborhood of x. So this is the precise definition of the convergence of real numbers. Right. For example, if xn equals to 1 over n, then xn may look like this. Right. So this is xn. And this one goes to 0. So meaning that if you draw an epsilon, and this epsilon can be arbitrarily close to 0. No matter how small this epsilon is, eventually, after a certain point, this is an epsilon. After this point, the entire sequence will be within this epsilon neighborhood of x. Right? In this case, the x is the x-axis. X is 0. And so after this point, the entire sequence is going to be staying within this epsilon neighborhood. And because this epsilon is can be arbitrarily small, so if you push this epsilon to be arbitrarily close to 0, intuitively the sequence will be getting closer and closer to x, and eventually converges to x. So this is the precise definition of real numbers. And the convergence of random variables is going to be defined based on this definition, because for random variables, they map everything to real numbers. So in the end, we are going to deal with a sequence of numbers. Okay. So the first type of convergence, so I think today I will only cover the first type of convergence. It's one of the strongest convergence type of random variables. We call it almost sure convergence. Convergence or convergence with probability 1. Okay, these are different statements, but they are defining the same thing. Okay. So we say that a sequence of random variables converges almost surely or with probability 1. Like these are two different ways to state this convergence behavior. We say this xn, the sequence of random variables, converges almost surely to a random variable x if the following holds. So first of all, the notation is to write that xn, the sequence of random variables, right, converges to x. But in what behavior? In what type of convergence behavior? In the almost sure type. Okay, we write a dot s dot for almost surely. Okay, so this is the notation. Xn, the sequence of random variable, converges to x almost surely. What does this notation mean? It means that the probability of this event equals to 1. This is the event. You can view this as event E. And this event E looks a little bit weird because it says that limit xn equals to x. But this is not that precise. Let's precisely write it out. This event E, because this event E is only defined, it's only denoted in the notations of random variables. We know that we always want to go back to the original outcome space, right? So this event, let's translate this into that language. So this event, precisely this event means that we're looking at the set of all outcomes right? Set of all outcomes from the omega space, right? We collect the set of all outcomes omega such that the realizations of this sequence of random variables on this outcome converges to the realizations of the random variable x on this outcome. Now, okay, what does this mean? So basically, if you look at this limit, it is well defined because x omega is a real number, right? Because this random variable x, the target random variable, it's a random variable that maps omega to a real number. So this is a number. And the left-hand side, basically, it is a sequence of numbers, right? Xn omega. Each xn will map omega to a number, small xn, right? So this is a sequence of real numbers. And this criterion says that, okay, so this event basically collects all the outcomes such that on this outcome, the sequence of realizations of xn will converge to x omega. This real number will converge to the real number x omega. You can, based on this criterion, right? You can examine all the outcomes one by one throughout the omega space. You collect all those omegas that satisfy this criteria into this event E. Right. So that is how this event E is defined. We can intuitively look at this, understand this convergence definition in this picture. Okay. So let me put it here. So this is the omega space, right, between 0 and 1. That's the x-axis. And now defined, all this sequence of random variables are functions defined on this omega space. Right, this is x1, x2, and x3. in the end, we have maybe an xn, x, right? The target random variable. Okay. So how do we look construct? How do we get this set E? How do we get this set E? We look at all the omegas such that this limit holds. So basically, we go over all the omegas. Pick this omega, for example. I'm going to look at whether or not this omega belongs to this set E. Basically, I just need to examine this criterion. So this criterion says that, okay, now you look at the sequence of realizations of this random okay, you look at all the realizations of this sequence of random variables on this under this omega. And this is x1 omega. Take this value. This is x2 omega. These are real numbers. You pick all this sequence of real numbers, right? You have a sequence of real numbers under this outcome omega, small omega. Right? You look at this sequence of real numbers. If this sequence of real numbers converges to this number x omega, then we will put this omega into this set E. This means that, okay, under this outcome, the realizations of this sequence of random variables converge to the realization of x omega. So in the end, it is defined by the convergence of a sequence of real numbers. We collect all such outcomes into this set E, right? And almost sure convergence says that the probability measure of this set E is 1, right? If you think about the notations that we introduced before, we call if a set E has probability measure 1, we say that this event E happens almost surely, right? And in this specific case, this E is defined by all the omegas, while this sequence of the realizations of this sequence of random variables converge to the realization of the target random variable. Right? And such a set or such an event E has probability measure 1. Then we call this almost sure convergence. So the almost sure really comes from this definition. Right? Basically, if you look at intuitively to think about this, okay, basically it says that almost all the omegas, almost all different omegas, we will have this type of convergence. If you look at any arbitrary vertical, draw a vertical line that intersects with all these random variables. These points are the realizations of random variables under this omega. And the almost sure convergence means that for almost all these omegas that you consider, this sequence will converge to the target, to the realization of the target random variable. Right? So all these feasible omegas, they form a set that has probability measure 1. Okay. Basically, for almost all the outcomes over this interval, we have this convergence. So you can see that this convergence is very strong because it requires that this function, right, the sequence of these random variables converge to the target random variable for almost all the outcomes omega pointwisely. Right? So eventually, so for every single point omega, along this vertical curve, this sequence will eventually reach or converge to the target, to the realization of the target random variable. So no matter which omega maybe you can see that in this case, these random variables may be more flat, right? And this will converge to X quickly. And in this part of the omega space, maybe X1, X2 they have more fluctuations, but eventually they will also converge to the realization of X. So this almost sure convergence basically requires that the entire function, this entire sequence of function, converges over the entire domain pointwisely. It's a very, very strong requirement. Right, so this is notation, and this is the precise definition for almost sure convergence. And put it the other way, this means that, okay, this sequence of real numbers will converge to the real number X omega for all the omegas, except for a small set of outcomes that has probability 0. Because this probability has measure 1. So the complementary case is that for those omegas, well, this guy does not converge to X omega. Those omegas has probability measure 0. And I would like to spend, let's finish this simple example, since we are already here. So let's consider this example. Well, we have a sequence of random variables that indeed converges to X almost surely. So the random variable is defined, the function is defined in this way. Xn, the nth random variable, maps omega, right? This is the outcome between 0 and 1. Xn omega is defined as omega to the power of n. Right? Well, this omega is between 0 and 1. Now, precisely x1 omega is omega to the power of 1, so it's omega. X2 omega is omega square. X3 omega is omega cubic. Okay. We want to show that this sequence of random variables converges almost surely to 0. The target random variable x, this function is defined as x omega equals to 0 for all the omegas between 0 and 1. We want to show that xn converges to x almost surely. Now, how do we show that? Basically, we want to show that this set has probability measure 1. We collect all the outcomes omega such that xn omega eventually converges to x omega. Here's how we collect this set. We can observe that, so we know the target random variable is 0. Right? It's defined as a constant 0. And xn omega, if we fix omega, xn omega is omega to the power of n. We know that this sequence converges to 0 for all omega between 0 and 1. Right? For omega less than 1, greater than or equal to 0. Right? Think about that. If omega is strictly less than 1 and bigger than or equal to 0, then this sequence, because we are raising to the power of n, so if you raise this n to infinity, this is going to converge to 0, right? So basically, for any omega between 0 and 1, but not including 1, for all these omegas, we do have this convergence, right? We do match this convergence. Xn omega indeed converges to the evaluation of x omega. So this is the set that we are looking at here. This is the set. So this set is simply the set between 0 and 1, not including 1. Because now what happens at 1? If you let omega equals to 1, then this sequence is a constant sequence of 1. Right? 1 to the power of n is always 1. And this 1 does not converge to 0. Right? So this set does not include 1. Okay. So this is the set that we identified. And this is the set where this limit holds. The set of outcomes where this limit holds. And we can see that this set has measure 1. Right? The probability measure of this half closed, half open interval is 1. Because we are only excluding a single point on this interval, and that single point has intuitively it has length 0, but does not contribute to the probability mass. So indeed, we verified that the probability of this event is equals to 1. Okay? So we conclude that xn goes to x almost surely. Okay? So basically, you have to figure out this set first. The set of omega where xn omega converges to x omega. Once you figure out this set, you look at the probability measure of the set. If this is 1, then you claim almost sure convergence. Otherwise, it is not. Okay, so I think I will stop here. This is everything about almost sure convergence. And we have three other convergence types, and they have they are slightly different with each other. So sometimes it's a little bit confusing when we look at these definitions. But I think for each one, right here, we are defining everything precisely based on all the probability theory that we have set up in this semester. This is an event, right? This is a set of omegas is an event. We can evaluate the probability measure of this event.